When we picture major medical breakthroughs, uh, there's almost always this expectation of cinematic drama.
Right, like the neon lit lab and the glowing test tubes.
Exactly. You picture this sleep-deprived scientist holding up a vial shouting "Eureka"
Hmm.
while, triumphant music swells in the background.
It's a great visual. I mean, we love the idea of the lone genius making a sudden world-changing discovery.
We really do. But then you look at the source materials for today's deep dive. We're digging into your biomedical research notes, specifically focusing on Lecture 17, data management. And honestly, you quickly realize that the glowing vial is a total myth.
Yeah, the day-to-day reality of large-scale clinical trials is, well, it's mostly just spreadsheets.
Right. And welcome to the deep dive, by the way. If you're listening right now, you know that doing the research is really only half the battle.
The other half is actually proving it without messing up the numbers.
Exactly. So our mission today is laser-focused. We are doing a rapid-fire masterclass on Lecture 17. We're going to tackle 27 multiple-choice questions straight from the source material.
It's going to be intense, but it's crucial. I mean, data management sounds like dry admin work, but it's the foundation that keeps multi-million-dollar studies from just, falling apart.
Bad data management can literally cost lives. So let's jump right in. I'll read the question numbers, the questions, and the options, and you tell us the answer and why it matters.
Ready?
I am ready. Hit me. Okay, let's start with the blueprint of a database. Question 3 asks, what does a row represent? Option A is variable, option B is record, option C is identifier, and option D is data point.
The correct answer is option B, record. You have to think of a database like a digital filing cabinet, right? A row tracks one single observation. So in a human trial, that horizontal line is one specific participant's entire story.
Oh, okay, so everything in that row, like their age or blood pressure, belongs to that one person.
Exactly. It's a human life distilled into data points.
Which brings us to question 23. What does a column represent? A, variable, B, record, C, demographic, D, outcome.
That would be option A, variable. Because while the row is the person, the column tracks a specific piece of data like heart rate vertically across all the different records.
Right, because that trait varies from person to person. Makes sense. Now, obviously, privacy is a huge deal here. Question 5 is about identifiers. It asks, what must identifiers be? Option A, unique. Option B, maintained by an index. Option C, secured by QA. Or option D, all of the above.
It is definitely option D, all of the above. An identifier's entire job is to replace a person's actual identity so we can maintain anonymity.
So like calling someone patient 104A instead of John Smith.
Right, and it has to be unique and secured by quality assurance, or QA, because if you mess it up, you can't untangle the data later.
Which perfectly sets up question 21. Which of the following is false about unique identifiers? Option A, it can be the same for more than one participant. Option B, it maintains anonymity. Option C, it is maintained by a computerized index. Option D, it tracks individual records.
The false statement is option A. It can be the same for more than one participant. That is the one thing it absolutely cannot be.
Yeah, that would be a disaster. Okay, question 14 looks at the broader outline of data entry design. What is the logical flow? Option A, identifier, demographics, outcome, and exposure. Option B, demographics, identifier, exposure, outcome. Option C, outcome, exposure, identifier, demographics. Or option D, exposure, demographics, outcome, identifier.
The correct flow is option A, identifier, demographics, outcome, and exposure. It's basically how a researcher naturally thinks.
So you figure out who they are first, then what their baseline is.
Exactly. Who are they? What are their demographics? What happened to them? And what were they exposed to? It reduces the cognitive load when you're typing it all in.
Let's pivot to segment 2, the art of naming and coding these variables. Question 2 asks about variable naming conventions. Option A, they should be short. Option B, they should include spaces. Option C, avoid duplicates. Option D, A, and C.
That's going to be option D, A, and C. You want them short, and you definitely want to avoid duplicates.
Okay, question 13 expands on this. What are the rules for naming variables? Option A, keep them short with no spaces. Option B, make them consistent. Option C, clearly refer to the questionnaire. Option D, all of the above.
It's option D, all of the above.
Okay, I have to push back here for a second. Why can't I just name a variable whatever I want? Like, why no spaces? That seems like a weird rule from the 1980s.
I get that a lot, but statistical software like SPSS or R, they will literally choke on a space.
Wait, really?
Yeah, they read a space as the end of a command. So if you name a column blood pressure with a space, the software looks for blood, gets totally confused, and crashes your analysis. You have to use underscores.
Wow, okay. Good to know. Let's talk about coding the answers inside those columns. Question 27 asks, what type of variable is this? Have you ever smoked? 1. Yes. 2. Is it option A, categorical, option B, continuous, option C, ordinal, or option D, numerical?
That is option A, categorical. Let's drop the jargon. Categorical just means the data falls into distinct non-overlapping buckets. You either have smoked or you haven't.
Got it. Now, question 8 asks about the rules for coding those buckets. Option A, prefer numerical coding. Option B, use letters. Option C, decide on missing values beforehand. Or option D, A and C.
The answer is option D, A, and C. You want numbers, and you absolutely must decide how to handle missing data before you start typing anything.
But wait, if it's a yes or no question, how do you use numbers? Question 15 actually touches on this. It asks, what is false about coding? Option A, you should be consistent. Option B, you should document your codes. Option C, prefer numerical coding. Option D, coding with 1 and 1 should be avoided for dichotomous variables.
The false statement is option D, coding with 0 and 1 should be avoided for dichotomous variables.
Oh, so question 25 is basically the same thing, but it's a true or false. True or false, coding with 0 and 1 should be avoided for dichotomous variables. Option A is true, option B is false.
The answer is option B, false. In fact, using 0 and 1 is the absolute gold standard in biomedical research.
See, that's wild to me. I would just code yes as 1 and no as 2. Why is 0 and 1 so much better?
Because of how the analytical software does the math later, a 1 means the trait is present, a 0 means it's absent. So if you run a formula to see how a disease impacts something else, multiplying by 0 completely zeroes out the healthy patients.
Oh, wow. It just removed them from that specific calculation automatically.
Exactly. It makes the back-end math incredibly clean. If you used 1 and 2, the software would assume the no patients had twice the value of the yes patients, which is mathematically absurd.
That is brilliant. Okay, let's move to segment 3, which is all about the rulebooks. Question 26 asks, what is false about a data dictionary? Option A, it is created after the data entry is started. Option B, it contains all the values assigned to variables. Option C, it gives a brief description of variables. Option D, it acts as a guide.
The completely false statement is option A, it is created after the data entry is started.
You have to do it before that.
You absolutely must. The data dictionary is basically the Rosetta Stone of your research. If you start making up codes on the fly, you'll end up with total chaos. You write the rule book before you play the game.
Makes sense. Question 19 is about the data catalog. What is incorrect about the data catalog? Option A, it is highly useful for sharing data. Option B, it describes variables for future reference. Option C, it helps maintain continuity. Option D, it is advisable to exclude the missing values from the data catalog.
The incorrect statement is option D. It is advisable to exclude the missing values from the data catalog. You should never, ever do that.
Why not? If the data is missing, isn't it just clutter?
No, because missing data is still data. If 30% of your patients skipped a specific question, that tells you something critical about your study design. If you hide that by excluding it, you're essentially falsifying the reality of the trial.
Right, you're hiding the flaws. Okay, question 12 is about complete data documentation. What does it actually include? Option A, just the variables. Option B, just the structure. Option C, structure, variables, history, and storage information. Or option D, only the backup history.
Complete documentation is option C, structure, variables, history, and storage information. Science has to be reproducible 10 years from now.
Which leads right into question 18. What does storage information entail? Option A, just the location. Option B, just the media. Option C, media, location, and backup information. Or option D, security passwords.
It's option C, media, location, and backup information. Because if you don't know exactly where the nightly backups live, a single spilled cup of coffee on a server could wipe out a decade of research.
Okay, so speaking of human error, let's look at segment 4. Quality assurance, or QA, catching those errors before they multiply. Question 4 asks, what QA specifications should be checked? Option A, minimum and maximum values. Option B, legal codes and skip patterns. Option C, odd coding. Option D, A and C. Actually, wait, the notes say the answer involves all of them. Let's just say option D is A and C representing all those things.
Yeah, the answer is option D, A, and C, meaning you check min-max values, legal codes, skip patterns, and auto-coding. The database needs to actively fight back against bad data.
Question 22 hits this from the other side. What is not a QA measure? Option A, setting minimum values. Option B, using legal codes. Option C, avoiding skip patterns. Option D, auto-coding.
The answer is option C, avoiding skip patterns. You want to use skip patterns, not avoid them.
I thought skip patterns were just to save time for the clerk, like skipping sections that don't apply.
They do save time, but it's really about integrity. If the system knows a participant is biologically male, a skip pattern automatically locks out the question asking how many months pregnant they are.
Right, because if someone accidentally typed a 2 in there.
Your whole data set becomes a joke. Reviewers will look at it and say, if men are listed as pregnant, what other massive errors are hiding in here?
That makes total sense.
Yeah.
Question 7. What does data collection instrument design encompass? Option A, formatting. Option B, phrasing. Option C, sequencing. Option D, all of the above.
It's option D, all of the above. How the form looks and flows dictates how accurate the data entry will be.
And question 16 is a true or false. True or false? Data entry is an opportunity to partially clean data. Option A is true. Option B is false.
Option A, true, because passing data through all those QA rules cleans it in real time.
Okay, here is the question that blew my mind when I was reading the notes. Question 17. True or false? In a diabetes study where expected blood sugar is 50 to 150, coding a missing value as 99 leads to an erroneous result. Option A is true. Option B is false.
This is such a classic example. The answer is option A, true. It leads to a catastrophic result.
Explain this because it perfectly illustrates why QA and coding matter so much.
Okay, so you need a code for when a patient misses a blood test. If a lazy researcher just says, just type 99 if the test is missing, the software doesn't know 99 is a secret code for missing.
Right, the software just sees the number 99.
Exactly. And in a diabetes study, a blood sugar level of 99 is a perfectly healthy, normal result. So if 50 patients miss the test and the clerk types 99 for all of them, the computer thinks 50 patients are suddenly incredibly healthy.
That's terrifying. It makes the experimental drug look like a miracle cure when they didn't even take the test.
Precisely. You could literally push a useless drug to market based on a bad placeholder code. You always have to use an impossible number like 999 for missing values.
Okay, let's move to segment 5, which gets into the advanced structures. Question 6 asks about the key elements of data management. Option A, defining variables. Option B, designing data dictionaries. Option C, quality assurance. Option D, all of the above.
Definitely option D, all of the above. It takes all those pieces working together.
Now, what if this study is massive, like an entire country? The notes talk about mother and daughter databases. Question 9 asks, can you store info at various levels, like village, household, and individual in separate databases, and link them? Option A is true. Option B is false.
The answer is option A, true. This is how you avoid typing the same village data 1,000 times for 1,000 different patients.
Which leads to question 24. What is false about mother and daughter databases? Option A, they reduce redundancy. Option B, they're linked by a common index. Option C, they store data at various levels. Option D, each database cannot have its own unique identifier system.
The false statement is option D, each database cannot have its own unique identifier system.
Oh, so they can have their own IDs.
Yeah, absolutely.
That-
The individual has a patient ID, the house has a dwelling ID, but they are linked by a common key. It's like how your social security number links your bank account and your tax records, even though they use different internal numbers.
Okay, so question 10 and question 20 in the notes are actually identical, and they ask about this exact concept. What is not true about a normalized database? Option A, it minimizes redundancy. Option B, it organizes data efficiently. Option C, a normalized database does not facilitate further data aggregation. Option D, it connects related tables.
The statement that is not true is option C, a normalized database does not facilitate further data aggregation.
Because normalization actually makes aggregation easier, right?
Exactly. Normalization just means every piece of info lives in exactly one place. If the village changes its water source, you update one single cell in the mother database, and it instantly updates for all the thousands of patients linked to it.
That is incredibly efficient. Okay, final stretch, segment 6, the life cycle. Question 1 asks, what are the steps in data management? Option A, defining variables in dictionaries. Option B, entering and correcting data. Option C, backup and archives. Option D, all of the above.
It's option D, all of the above. It's a very rigid chronological pipeline.
Right, which makes question 11 kind of funny. A postgrad researcher just finished her data collection. What should she not do during the data management phase? Option A, applying for the ethics committee clearance. Option B, creating the database. Option C, doing backups. Option D, running QA.
She definitely should not do option A, applying for the ethics committee clearance.
It is way too late for that, right?
Way too late. I mean, you can't ask for permission to experiment on human subjects after you've already collected all their blood and data. ethics clearance happens years before you ever touch a spreadsheet.
It's the ultimate cart before the horse mistake.
Exactly. By the time you hit data management, you are just protecting the data you ethically gathered.
Well, we survived the gauntlet. We made it through all 27 questions for Lecture 17. And I think the biggest takeaway here is that data management isn't just shuffling numbers around in Excel.
No, not at all. It is the invisible armor that protects scientific truth. Without QA, dictionaries, and proper coding, the data is just noise. And you can't cure diseases with noise.
That's incredibly well put. Before we wrap up, we started by talking about that romanticized view of science, the glowing vials and dramatic breakthroughs. But the real lesson today is about the unsung heroes sitting at their computers, making sure a missing value isn't typed as a 99.
It's true. The diligence of a data clerk is just as vital as the brilliance of the lead scientist. And, I'll leave you with this final provocative thought to mull over.
Let's hear it.
If a single misunderstood code like using 99 for a missing test can completely alter a life-saving clinical trial, how much of the scientific truth that you rely on every day is ultimately just the product of a really well-maintained spreadsheet?
Oh, wow. That is a sobering thought to end on. Remember, science is only as good as the data that proves it. Keep learning, keep questioning the data, and we'll see you on the next deep dive.